All right, campers, now we're going to throw in those complex zeros and look at the fundamental theorem of algebra, which is, to me, kind of funny that we're looking at the fundamental theorem, like the most basic, like foundational theorem of algebra, right at the end of chapter 4. You'd think it'd be a little earlier, but guess not. Okay, so a complex polynomial, it still has the same format as a regular polynomial in the real number system. However, the difference is those coefficients, they're now able to be a complex number. Whereas before, they could only be integers or real numbers sometimes. So that's the difference. So a complex number z is called a complex zero if f of z is equal to 0. Okay, so here's the fundamental theorem of algebra. Every complex polynomial function of degree n greater than or equal to 1 has at least one complex zero. This could also be interpreted as every polynomial of degree n has exactly n complex zeros. So with the reals, for the real zeros, it could have up to n real zeros, but now since it's the complex, it will have exactly n complex zeros. So like example 1, how many complex zeros do the functions have, and then what are they? In example A, the degree is 2. So we are going to get 2 complex zeros. And what are they? Well, if you set this equal to 0 and solve for x, that would be plus or minus 2. So they don't have to be imaginary to be a complex number. The imaginaries and the reals together make up the entire complex number system. But over here, in example B, the degree is 2, so there's still 2 complex zeros. But now if you set it equal to 0 and solve for x, you would get plus or minus 2i. So sometimes they come out as real numbers, sometimes they come out as imaginary, sometimes you get a combo, but they're all complex. All right, let's look at the conjugate pairs theorem. This is a good little theorem to know. So let f be a polynomial function whose coefficients are real numbers. So if z equals a plus bi, if that's a 0 of f, then the complex conjugate a minus bi is also a 0 of f. So that's kind of cool, because if you know one imaginary or one complex 0, then you'll automatically know a second just by doing the complex conjugate. So you're just flipping the sign on the imaginary part. So example 2, find the remaining zeros of f. So it has a degree 3, so there are going to be 3 complex zeros. So there's 1, 4. Here's a second at 3 plus I, so there's a third. Well, it's got to be the conjugate of that. 3 minus I. Part B has a degree of 6, so there's going to be 6 complex zeros. Well, we have 3 of them, and they're all imaginary, so just get their conjugates. So 2 plus I, 3 plus 4i, and then this one here, even though there's no real number, it's missing the a, you still flip the sign on the imaginary, so that would be a negative 8i. So those would be your 3 additional zeros, or remaining zeros. All right, example 3, find the complex zeros of each function. So this one, not too hard to do. If you set that equal to 0 and solve for x, that would just be plus or minus I. If you set this one equal to 0 and solve for x, you could factor it, you could move over the 16 and fourth root it. Either way, you're going to get plus or minus 2, as well as plus or minus 2i. Okay, I'm going to stop the video here and pause it, and then we'll finish the section and the chapter in the next video.